Hello and welcome to this on-demand presentation on path tracing. My name is Ahmed Abdelsalam. I'm a software engineer from the segment routing team at Cisco. And in this presentation, I will try to introduce in a simple way what is the problem that we are going to solve and how we solve it. And at the end, I will provide a demo that includes several hardware platforms supporting path tracing. And always with the segment routing project, we go back to the root. We go back to the purity of IP and we ask naive questions. And the question here is, how come that if you have a packet from A to M, you don't know, and I think most of you, but maybe all of you, you don't know how this packet went from A to M. From a reality point of view, you don't know. Because there can be several valid passes. Here in this example, you have 7. All of them are possible. But which one has been taken, likely you don't know. But it could very well be that there is a bug or fib corruption somewhere on the path, and the packet is taking another path, the red one. You wouldn't know either. Path tracing is a solution to this problem that not only gives you a deterministic solution to tell you on which path the packet has been forwarded, but also the timestamp at each hop and the interface load on each hop. The most important thing is that to make it work, you need to monitor in the most basic packet pipeline of the router. Any solution that would punt the packet to the line card CPU or any NPU coprocessor or any kind of process that would not use the same forwarding tables as your customer packet is not useful. All of these ideas have been engineered to be implemented in the basic pipeline at line rate effective for any packet. To show in a very simple manner how this technology works, let's take this very simple example. I'm going to create a probe packet from router A destined to router M. On this packet, we have the base IPv6 header with source address equals A and destination address equals M. Very simple. And following this IPv6 header, I will have an IPv6 hop-by-hop extension header. This is one of the extension headers which was defined in RFC 2460 more than 25 years ago. In this hop-by-hop header, we have a path tracing option, which is basically a metadata scratchpad. So it is going to be a space where each router along the packet path will write a tiny piece of information. This tiny piece of information, we call it midpoint compressed data. The midpoint compressed data is a 3 bytes of information where we are encoding the outgoing interface ID, the outgoing timestamp, and the load of the outgoing interface. Somehow you can see this like a passport. This is the analogy that we use sometimes. Because as the packet traverses the network, each one of the router is going to stamp his information in this passport. In the same way, a traveler will have his passport stamped at each transit airport. So router A is going to generate the probe packet, and just before putting the packet on the outgoing interface is going to stamp this packet with its midpoint compressed data. Well, the packet has been forwarded on the interface connecting node A to node B. It is being forwarded at this particular time, and the load in this interface was this value. Then the packet is sent out. The packet arrives at router B. I'm going to do all of my lookups, and just before putting this packet on the outgoing interface, I'm going to do the same as I did at router A. I'm going to stamp this packet with my midpoint compressed data. So this packet has been forwarded on the interface connecting node B to node G. It has been forwarded at this particular time, and this is the load I'm seeing on that interface. And the process goes on. The packet arrives at router G. I do all of my lookups, etc. And just before putting this packet on the outgoing interface, I'm going to stamp this packet with the outgoing interface information, timestamp, and load. So the basic intuition here is to have full visibility into the actual passes taken by packets in the network. And on top of this visibility, we are going to add the timestamp information and the load at each interface so that we have full characterization of the packet delivery path in the network. The full characterization is achieved with the minimum MTU overhead by having each midpoint recording only 3 bytes of information. And at the end, you will be able to know how the packet is being routed and the state of each router on the packet delivery path. You will have this information in real time so you can know the current status of the network, but also we will be recording this information in a time series database so you can look up the state of your network at any point in time. Again, to make path tracing work, we need to monitor in the most basic pipeline of the router. So one of the key principles of this project is to extract the juice out of the router and get the most out of the router capabilities so that we can do everything at line rate in the regular MPU. We don't want to use any kind of coprocessor. No, because we want to get the real data. And to get this real data, we need to experience the same path and use the same forwarding tables as any customer packet. For this reason, we have been working with many different platforms to optimize the data plane up to every detailed micro instruction to accommodate for the limitation of different ASICs and make sure it works at line rate across all of these different ASICs. And you will see later the list of platforms that support path tracing, which is quite impressive. In particular, we optimize the data plane such that it requires the minimum MPU parsing, the minimum number of read and writes instruction, and the minimum depth of packet editing. We also made sure that the path tracing headers are always at fixed offset in the packet and also avoid any header insertion or resizing. And obviously, we had to minimize the MTU. We minimized the hardware complexity by doing a good engineering of the data plane. But we also minimize the hardware complexity by leveraging SDN analytics. If we go back to the previous example, the probe packet in blue that was going from A to M. When the packet gets to M, the typical approach was to process the data collected in the probe packet by the CPU of node M. But this approach does not scale. The router CPU is not intended for use for this kind of processing. And if you use the router CPU to do such processing, you will end up overloading it. Instead, we take a more scalable approach by forwarding the path tracing data to an SDN application. We can forward the probes from node M to the SDN application at line rate using a new simple data plane behavior. And we get a better scaling by leveraging an SDN application running on a compute node. On this SDN application, we are going to do all of the analytics, such as translating the list of collected interface IDs into an actual path, but also deducing the time, the load history at each hop, and we highlight what we consider as hotspots. Also in this SDN application, because it has communication with the path computation element, PCE, we can do quite interesting things. For example, from the PCE, we can get the list of expected passes which will be based on the control plane information and compare this list of passes to the actual passes seen by path tracing, which reflects the actual hardware forwarding. In the analytics, we can show any inconsistency between the expected passes you get from the PCE and the actual forwarding passes detected by path tracing. So if you wish, you can check the inconsistency between the routing and the hardware forwarding, which is quite interesting. And as always, we work on building the ecosystem. We shared this idea with Broadcom, with Marvell, extremely good feedback from these partners. Path tracing is something that at Cisco we will be shipping in this calendar year. And today we have it running on Cisco NCS 5700 based on Broadcom Jericho 2. We have it running on the Cisco 8000 series based on the Cisco Silicon One ASIC. We have it also running on the ASR 9000 based on the Cisco Lightspeed ASIC. And we have implementation in Marvell. We have seen also a strong interest from several operators. Some of these operators are already testing this technology in their lab. And as always, we worked with our partners in academia in order to create an open source ecosystem. And we have implementation of path tracing in the Linux kernel, FDIO VBP, P4, and many others. And obviously, we have released this idea to IETF for standardization. And if you want to learn more about path tracing, there will be a detailed talk on path tracing at Nanog 85 in June by Mike Valentine from Goldman Sachs. I think by now it's quite obvious the value of path tracing when compared to the other solutions. But let me remind the benefits of path tracing. Path tracing has the lowest MTU overhead, only 3 bytes of information at each hop, compared to other solutions such as INT, IFA, etc., which requires orders of magnitude of that number. The headers processing in path tracing is far simpler compared to other solutions, which would require a header resizing, etc. at each hop. Plus, in path tracing, the header is always at the same offset in the packet, compared to other solutions where the header offset will depend on the packet type, VXLAN, NSH, UDP, GRE, etc. And because of the data plane simplicity of path tracing, it can be supported at line rate across a wide range of ASICs. This is already proven by the current number of line rate implementations that we have shown. And finally, path tracing provides the most accurate data because it is implemented in the most basic hardware pipeline. To conclude, simplicity always prevails. Path tracing provides a deterministic solution to tell you on which path the packet has been forwarded, plus the timestamp and the interface load at each hop. It is implemented in the most basic router forwarding pipeline. Line rate for any packet with the lowest MTU overhead compared to other solutions. Path tracing enjoys a rich ecosystem of different ASICs, multiple operators, as well as open source. And now it's demo time. In this demo, we have built a lab using the various hardware implementations of path tracing. As you can see here, we have a quite impressive number of line rate hardware implementations of path tracing. We have the Cisco ASIR 9000 based on the Cisco Lightspeed ASIC. We have the Cisco 8000 based on the Cisco Silicon One ASIC and programmed in P4. We have the Cisco NCS 5700 based on Broadcom Jericho 2 ASIC. And we have the Cisco Nexus N3000 based on Barefoot Tofino and programmed in P4. And we have a Marvell device running the Prestera Falcon ASIC. In this demo, we generate probes from the SFO router towards New York. These probes are going to be hashed over the ECMP passes. Each node is going to record its midpoint compressed data in the probe packet. The midpoint compressed data are 3 bytes that represent outgoing interface ID, load, and timestamp. The New York router is going to forward these probes using a new data plane behavior at line rate to the SDN application. In the SDN application, we are going to analyze the probes to show the different ECMP passes and the information of each pass. With this, let me jump actually to the demo. We have a few interesting dashboards that we can leverage to visualize the path tracing data. Let's actually start with the ECMP discovery dashboard that we see here, and this is where we are going to visualize the ECMP passes. In this ECMP discovery dashboard, we have the network topology of the demo composed of 6 routers running different ASICs that support path tracing. We configured a path tracing session on the SFO router to send probes to measure the ECMP passes between SFO and New York. Each router on the path from SFO to New York records its midpoint compressed data in the probe. At New York, we forward these probes to the SDN application. The SDN application collects these probes, analyzes them by translating the list of recorded interface ID into an actual path, deduces the timing and load history at each hop, etc. The SDN application will save these results of the analytics in a time series database. So I'm going to select SFO as source, New York as a destination, and I will leave the traffic class to the default. We can also choose to show the ECMP passes for a given point in time. For example, here I'm going to show the ECMP passes for the last 30 minutes. The SDN application in the backend will provide us a list of ECMP passes that was detected in the last 30 minutes, and it will show them on the right panel we have here on the dashboard. As you can see, path tracing detected that in the last 30 minutes we had seen these 4 ECMP passes. We can click on any of these passes to show the list of traversed interfaces for that path. The dashboard will also highlight the path on the topology, as you can see. The SDN application can also have access to the information in the path computation element and can compare the list of passes seen by path tracing to the list of expected passes seen by the PCE. Then it can, for example, color the passes to highlight the expected versus the non-expected passes. We will have other demos in the future to show you how the SDN application can provide such inconsistency checks. Now we have been able to discover all of the ECMP passes. Let's see how path tracing can show you the status of each one of these ECMP passes. And let me jump to the second dashboard, the ECMP monitoring dashboard. We can select the source node, the destination node, the traffic class, and the period of time. So I'm going here to choose the same parameters as before. So SFO as source, New York as a destination, traffic class to default, and the last 30 minutes. And once we do that, the SDN application in the backend will provide us all of the details of each one of these ECMP passes. And it will plot this information on the different graphs that we have here. So we can see the different percentiles of delay, jitter for all of the different ECMP passes. And if we click at any point in time, we can have the list of the passes and the latency percentile for each one of these passes, as you can see here in the illustration. We can also do the same for jitter. Select any point in time and see all of the different passes and the jitter values for that passes at that time. So in this demo, we saw how path tracing can provide us the list of ECMP passes between any two nodes at any point in time. We also get the status of each one of these passes. We have the delay, the jitter of that pass. We can also highlight any inconsistency between the expected passes computed by the PCE and the actual hardware forwarding passes detected by path tracing. Thank you for watching this presentation and this demo. And for more information on path tracing, please visit segment-routing.net.